ridge. It's moving away from the ridge. We have documentation. We have proof that it's happening. Again, we don't have any driving force, but we have proof that it's happening. Well, in the 1970s, the Geologic Survey had a satellite, EROS, Earth Resources Orbiting Satellite, as we said. And they put markers on various areas of planet Earth. And the technology was such that they could ascertain any change in distance between those markers. And now they have actually taken and measured how fast things are moving apart, precisely. And we know that the fastest movement is about 10 to 12 inches per year. Doesn't sound like a lot, but multiply it by 1 million years and you've got some substantial movement. The North American plate is moving at the slowest rate, less than 1/2 inch per year. So in your lifetime, normal lifetime, it's going to move 40 inches, 3 feet. May not seem to be spectacular, but over 1 million years, it's some real sizable movement. So they've been able to document the movement with the Earth Resources Orbiting Satellite. And somewhere in, I think, your textbook, it might be this one, hold on. There it is. Indicates relative amounts of movement. The centimeters per year. 18.3, 17.2, 2.3. So they have measured precisely how much these things move on an annual basis. And so we have that evidence. But still, the jury is out. How does this happen? What's a conventional cell? What's a conventional cell?
Where the material goes down and goes up.
The other one, okay. Conventional cell, we talked about it with climate. Warm up, cool down. Warmer rises, colder sinks. Okay, so they propose that maybe what we have in the mantle, in the lower mantle, are a series of conventional cells. That heat rises in the mantle, lower mantle, to the asthenosphere, base of the asthenosphere, moves along the base of the asthenosphere, and then sinks. So this is a proposal that we have all of these conventional cells. And anything that's on top of this stuff is going to move as the conventional cells move. So we have the asthenosphere here. On top of that, we have the upper mantle. And on top of that, we'll have the crust. So the asthenosphere is the solid that shows flow characteristics. It's being exposed to high temps. It's moving out. It's being displaced. And as it's being displaced, everything on top of it is going to go with it. It's like having a bunch of material on a rug, and you pull the rug. Everything on top of that rug is going to go with it. Much like you're on planet Earth. As the asthenosphere moves, everything above the asthenosphere will move. Great idea. Prove it. Great idea, but prove it. How would you prove this? Remember, we're looking at units that are several miles below the surface. How would you prove something like this?
Well, how did they find out about the astrosphere?
How do they find out about the astrosphere? Something we'll cover a little later, but earthquake waves. We find that earthquake waves travel at certain velocities through certain materials, and when those waves hit where the astrosphere is, all of a sudden there's a reduction in velocity of the waves. And so they knew that it was something that was a semi-fluid, solid black that had flow capabilities. And we'll look at that probably next slide. Okay, here we are. How do you prove it? Where would you find the highest temperature in that convectional cell? Where it comes up or where it goes down? Where it comes up. We would anticipate the highest temperature should be here. And as we went this way, what should we anticipate? Temperature should drop. Now, the problem is, how do you put a thermometer in something like this? Very careful. They actually went to the bottom of the ocean, on their crust, and began measuring what they call heat flow units. Heat flow units are very, very minor temperature changes. I mean, hundreds of degrees. And what they found here is literally exactly what you said. High temp here, and as you go out this way, the temperature drops, and at the trenches, we had the lowest temperatures. At the rift zone, where this is coming up, you had the highest temp, and at the trenches, the lowest temp. So it appears as though what we're looking at is a series of convectional cells. So if we were to look at planet Earth, we have a whole series of these convectional cells. And at points like this, we're pulling apart where they pull apart, you have what are referred to as divergent plate margins. You rip apart. This one's moving this way, this one's moving this way. So up here you have convergent plate margins. And in all cases, we have convergent and divergent plate boundaries. We also have volcanic activity. Both of these are related to volcanic activity. Both of these are related to earthquake activity. So these are earthquake and volcanic zones. Okay, now Wegener has been accepted, his ideas have been accepted, and we now know how these things move apart. The scientific community, and I mentioned this before, the scientific community rarely jumps onto new ideas wholeheartedly. You have to provide evidence. You have to provide support. The scientific theory literally requires it. Now, are we absolutely, positively sure that that's the driving force? about 90%.